sure. All right. My name is Tracy Carroll. I'm with the Naval Surface Warfare Center, Carderock Division, and this is the final project summary for project WP-1671, solid separation and concentration of shipboard wastewaters and residuals by a high shear rotary membrane system. Also on the line are the rest of our team. We've got Dr. Brian Reed from University of Maryland, Baltimore County, John Bendick, former grad student of UMBC under Dr. Brian Reed, also Patrick Morrow from NSWC Carderock, Bill Hertel from NSWC Carderock, and Steve Balin from NSWC Carderock.
Oh, and Keith Legg here. I managed to call in.
Oh, okay. So I'm going to move on to slide 2. And so this project was initiated in FY 2009. The statement of need that it addressed is the advanced methods for removing solids from shipboard waste streams. And so currently membrane systems are used on board ships to treat bilge water, and in general in industry, membrane systems are also used to treat many different things to enhance product recovery and as well as improve product quality. One of the issues that membrane systems have to deal with is the accumulation of solids at the membrane surface. This reduces permeate flux, and so what conventional cross-flow systems do is that they will pump the waste at high flow rates parallel to the membrane to scour the surface. But this can become difficult if as your feed gets thicker and your waste concentration is high. They also operate at higher pressures to sort of overcome this solids accumulation at the surface. But this actually also kind of makes the solids accumulation issue worse because of it can compact the solids. It can lead to pore plugging and things like that. So our project, which is looking at the high shear rotary membrane system, rotary membrane systems consist of a stack of rotating membrane discs, and they create the scouring action by rotating the disc. Since the feed pressure and flash delivery is decoupled from the membrane scouring action, rotary membrane systems can operate at lower pressures, and they have demonstrated the ability to separate and concentrate solids in various wastewaters to concentrations as high as 35 to 40% solids. Okay, moving on to slide 3. So our technical objectives for the project was to develop a robust shipboard system to treat a variety of Navy solids-bearing wastewaters and residuals. We did this by looking at increasing the active membrane packing density, by using larger diameter discs. Also looked at backpulsing and continuous surface cleaning as ways to increase the permeate flux and therefore decrease system size. Using what we had learned, we would conceptually design, fabricate, and test a prototype shipboard HSRMS that would incorporate whatever combination of backpulsing, continuous surface cleaning, and larger discs that would work the best for the different weights. And with our outcome, or our goal was to produce a prototype shipboard rotary membrane system that would have increased waste treatment throughput, a smaller footprint / space requirements, and also be potentially portable. So the figure at the top right shows what a rotary membrane system looks like. It shows a stack of discs mounted on a hollow shaft. And this particular design uses stationary turbulence promoters in between each disc. We also refer to these as wagon wheels. And so this enhances the turbulence and then therefore the surface scouring. The feed would be outside the membranes, and then the fluid that permeates the membrane would flow through the interior of the disc through channels to the shaft, and then from the shaft it would exit the system. So the driving force in membrane systems is pressure, and for rotary membrane systems, they have a different pressure profile than traditional cross-flow systems. The graph on the lower right will help illustrate this. So the driving force is the pressure that the membrane sees, and so that is we call that the transmembrane pressure, which is the difference between the feed pressure or the applied pressure, which in the graph is at 60 psi, and then the back pressure that's induced by the membrane rotation, and that would be the bottom line starting at a little below 0 and dropping down to negative 60 or 70 psi. And so the back pressure is induced by rotation, varies with radius as well as rotation. So in this example, it was done for about a 7-inch disc, and it rotated at 1750 RPM, which is on the high end of rotation in the HSRMS. And as you can see, as you get out to the outer edge of the membrane, your net transmitting pressure goes negative, which means that in that area of the disc, you'd actually have permeate being pulled from the clean side back into the feed. So, our first objective was, trying to increase the active membrane area. So while doing this, we have to consider rotational speed. As the graph shows, we want to avoid excessive back pressure at the outer edge, and there's also just the mechanical issues of rotating a large disc at a higher rotation. But when you reduce your rotational speed, you also decrease your surface scouring action, and which lowers your flux. And so we looked at continuous cleaning and backpulsing as ways to sort of replace that cleaning action that you lose at lower rotations. So through the course of the project, we did runs with the standard system, and then with the modifications, the continuous cleaning, the backpulsing, to see what the effects were. So slide 5 shows just the rough outline of our project. We started off with choosing the synthetic waste that we would evaluate our system on. We then identified and screened commercially available membranes. The membranes that showed potential moved on to high-shear rotary membrane system tests, baseline as well as the continuous cleaning and backpulsing. Taking what we learned from the previous tests, we then came up with a conceptual design of an improved rotary membrane system, and then we fabricated and tested a prototype of that. So for our technical approach, for each set of conditions that we were testing, we did a minimum of 3 runs. While we did these runs, the system was typically in recycle mode, where the permeate was returned to the feed tank. We cleaned the membranes between each run to return it to initial performance, and we used a 2-step process that was recommended by the rotary membrane system manufacturer, which is Syntec. So early on, we were doing separate runs for each condition, each rotational speed, each modification, and then midway through the project, we realized that we could reduce the number of cleanings by switching to a rotation step-down method, where we start off at the highest rotation for a given set of conditions and then step it down, and each time waiting for flux to reach steady state before switching to the next rotation. The things that we're measuring were permeate flow and quality. So for permeate flow, we used initially we were using a magnetic inductive flow sensor because our flow rates were high enough to be read. And we verified the accuracy at the beginning of the project, and it worked well. But once we switched to the smaller discs later in the project, the ceramic discs, their permeate flow rate was too low, and so we changed to a different flow meter, which initially appeared to be accurate, but as we progressed in testing, discovered that there were some significant variances in it compared to just a manual measurement of collecting volume of permeate per time. And so we switched just to doing manual measurements. When we converted our permeate flow rates into Flux, we always temperature adjusted it to 20 degrees C. And moving on to the next slide, slide 7. For permeate quality, we initially measured that using turbidity. And but once we started working with the ceramic membranes, we were able to get the ET35N, which is the Navy-approved oil content monitor, so we used that on our bilge water test, and then continued to use turbidity when measuring permeate quality for when we ran tests with other weights. The two pictures show the front side and back side of one of our systems. So I guess if you look at the picture on the right, you get the best view of everything there. So the feed would go through the feed tank, through a heat exchanger, which is hidden at the bottom. It would go into the membrane chamber, which is on the left side of the picture. Permeate would come out the bottom of the motor, that white section of the membrane chamber, and then it would, on its way back to the feed tank, it would go through a permeate reservoir, which we included in the design so that when we did the backpulsing test, we would always, we were sure to have only clean permeate going back through the membrane instead of, the chances of having some of the air that we were using to backpulse making it to the membrane. So moving on to slide 8, we have just a few pictures of what we use for continuous surface cleaning attachments. We use sponges as well as brushes, which are shown on the right. We also did some radial distance experiments by using hubs, which are the pieces that hold the membrane onto the rotating shaft, by using hubs of different diameters, as shown in the picture. So starting with slide 9, it's our project results. We, with input from the NASTY technical warrant holder for environmental systems, as well as the Carter-Rock Code 633, which is the liquid waste side, and 634, which is, among other things, solid waste, hazardous material, ship to shore. With their input, we identified 4 wastes to look at 4 Navy shipboard, current and future shipboard waste. And with their input, they were prioritized, with bilge water as the highest priority, black gray water as second priority, and then the ash water from the plasma arc waste destruction system, and biosolids, which would be the residual from future black gray water treatment systems. Those were tied as third priority. Slide 10 just shows some of the waste characteristics, the discharge limits, and also the what the environmental tech warrant holder and Code 633 and 634 identified as what they saw as the potential applications for the rotary membrane system. So for bilge water, they thought there could be two opportunities for it. It could either be used to treat bilge water to the discharge limit of 15 ppm of oil or less, or it could be sort of an add-on to the current shipboard systems, and it would just further concentrate the oily effluent from the current systems. For our test, we used the oil detergent and particles bilge water mixture that Code 633 uses to evaluate their systems. And the recipe is shown there. That's the recipe for what we call 1X. That was what we primarily used, although for some tests we wanted to see what a higher concentration would do, and so we used 10X concentration, and that's just basically 10 times what you see there. For black-gray water, they saw the rotary membrane system as a way to remove solids prior to the treatment system. For the PAWS ash water, also looking at it as a solid removal before discharging the ash water to the sea. And for biosolids, they saw it as the opportunity as being able to dewater the sludge that would come from future shipboard systems. So as I mentioned, so we would make our bilge water for the test. For the black and gray water, we would get those from wastewater treatment plants. Primarily, we got our black-gray water from the same plants that Code 633 uses for their tests. For the few occasions where we weren't able to coordinate our tests with 633's tests, we got black water from the Little Patuxent River wastewater treatment plant. So slide 11, we identified and screened a variety of membranes. For the first 4 membranes, the PTFE and stainless steel membranes, those are available as sheet membranes, and so we evaluated them using a stirred cell, which is shown on the right. For the 6 ceramic membranes that are made by Carafol, they come as discs already, and so they come in 3 sizes, but only the smallest size, the 6-inch diameter disc, would fit in our rotary membrane system, and so we screened them in the rotary membrane system using the 6-inch disc. Slide 12 shows the results for the PTFE and stainless steel membranes in the stirred cells, and as you can see, they all perform similarly, and had good permeate turbidities, and so based on that, we moved them all forward to rotary membrane system evaluation. Slide 13 shows some of the results from the 6-inch ceramic membrane. The graph actually shows the results of backpulse testing, which we sort of rolled into our baseline testing. And based on what we were seeing, they all had fairly high fluxes. Some of them had really great fluxes at the different rotations. They all produced permeate that met the discharge limit of 15 ppm. But based on the fluxes that we're seeing, how high they were and how consistent they were from run to run, we selected the 60 nanometer and 7 nanometer membranes to move forward to sort of full-size rotary membrane system evaluation. So we special ordered a 10.5-inch membrane from Carafol. Slide 14 shows the results of our continuous surface cleaning test. Overall, for all the membranes, the effective continuous surface cleaning really varied by membrane waste and rotation combination. For the stainless steel and PTFE membranes, we evaluated them with 1X bilge as well as the PAWS ash water. We chose those because bilge is the high priority waste, and PAWS because being the most abrasive, we thought we would get a good indication if there was going to be a problem with membrane wear due to the continuous surface cleaning. There are no problems with the membrane wear. However, we did not see and we did not see any improvement in flux with the sponges as well as with the brushes. As you can see below, the graph shows the pause with sponges and without sponges, and despite the huge difference in just visual appearance of the membranes with and without sponges, there's no change in flux. Slide 15 shows the effects of continuous surface cleaning on using the 60 nanometer ceramic disc and to treat bilge water. If you look at the left-hand side graph, you'll see that, so we did test with 2 rotations with and without sponges, 1150 RPM and 500 RPM. The flux of the flux with sponges at 500 RPM was essentially equivalent to the 1150 RPM no sponge flux. Which shows that the loss of cleaning action that you get at the lower rotation can be compensated for by using the sponges at lower rotations. There was no improvement with and without sponges at 1150 RPM. The graph on the right just shows a longer-term experiment where we did a sort of a concentration batch down using sponges operating at 500 RPM. And we started off with 1x bilge. And as you can see, as time goes on, the flux steadies out at about 200 for most of the experiments. That would be all the symbols. And as the concentration of the waste being processed creeps up, and it's only as the concentration of the feed starts to spike at about 11 hours that we see a slight reduction in flux, but still very good flux rate. So it shows that the vertical memory system with sponges is able to concentrate the waste well with still meeting permeate quality requirements. So looking on to slide 16, we did
just back up a little.
Yes.
So if you can go back to the slide, so at 12 hours or beyond, where that is starting to show a decrease in flux from 200 down to 150, what's kind of a limit? What are you looking for as to the time frame where you would need to take action and unclog the membranes or whatever?
So I think for the current shipboard systems, they're not, they're running for only part of the day, and then they shut down. And at the end of their shutdown, they'll do part of the shutdown procedure is to do a hot water flush to clean it out.
Okay.
So what we're seeing is we can have really high fluxes for that amount of time that they're processing, for that half a day or so or more, and then we've shown by you can clean the membrane and it returns back to its original performance.
What's the membrane cleaning process? Are you going to be talking about that at all?
A little bit. I mean, I can. So what we're using in our test was a two-step process. It was basically a detergent wash, and then flush with water, and then we did a citric acid wash, and then the water flush, and that was it. We also, and I'll show you near the end of the slide, I show the results of when we use the cleaning chemical that the shipboard systems use to regenerate their membranes. We use that as well, and it performed nearly as well as our two-step process. And I'm not going to show the results, but we also did do a few runs where we tried to mimic the shipboard process of running for half a day or so, and then shutting down, doing a hot water flush, and then starting up again. And we did not see we would see coming back on after that shutdown, we would see the membrane performance back up where it was initially.
Thanks.
Okay. So, okay, moving on. So we also did continuous surface cleaning with the 60 nanometer ceramic membrane treating black water, and as the graph shows on the right, so the triangles are with sponges at 500 RPM. The circles are without sponges at 500 RPM. So there was a benefit with the sponges. It wasn't nearly as much as what we saw with bilge water. As at 1150 RPM, with and without sponges, they are up around 170 gallons per foot square day. They're the squares. But for one of our with sponges 500 RPM runs, we did at the end of it just increase the rotation up to 1150 to see what would happen, and the flux increased to the 1150 RPM level. So we're not. So it seemed as though So I guess so that shows that we weren't seeing permanent fouling. It was something that could be easily removed with rotation. So we're not really sure why the sponges weren't doing as well for black water as they did for bilge. We also took some feed and permeate samples during these tests and sent them to an outside lab for analysis. We wanted to see how the rotor-membrane system affected the BOD, COD, and total suspended solids levels. And so our inlets, our feed and our permeate values are shown. For the samples that we took, all of the permeate levels were below either below the detection limit, which was also below the discharge limit, or obviously below the discharge limit. So it shows that the rotor-membrane system does have the ability to actually treat black water, gray water. Slide 17, backpulsing. The standard membranes that we got from Syntec, for the PTFE and stainless steel materials, their standard design isn't suitable for backpulsing because the membrane sheet can lift up when the pressure is reversed. So they worked on coming up with a way to to make sintered stainless steel membranes, which they did with their 0.5 micron membrane. They sent us several generations of these sintered stainless steel membranes, and we tested them. But for every one that we got, the permeate flux was low, the quality was low for both just standard baseline tests as well as with backpulse. And so we ended up not continuing the tests with the Syntec membrane. For the ceramic membranes, we evaluated backpulsing with the 6-inch membrane. So our parameters were the backpulse net pressure, which would be the difference between the backpulse pressure and the net transmitting pressure, with the goal of having it be overall negative across the membrane. Negative meaning that your permeate's going from inside the membrane to outside the membrane. We chose a backpulse duration of 2 seconds, and then we looked at different rotations, the effects of having a 1 minute long, a 2 second backpulse every 1 minute versus every 2 minutes, and then different backpulse net pressures or delta P's of 10 psi, 20 psi, and 30 psi. And as the end result was that the delta P of 30 psi had the greatest flux benefit. And we didn't see any differences in flux between a frequency of 1 and 2 minutes, and so we chose 2 minutes just to minimize the amount of permeate we might lose during the backpulsing. Slide 19. So for build water, we didn't see any backpulse benefit for either the 6-inch or the 10.5-inch 60 nanometer membranes. We tried doing a couple of different backpulse duration and frequency combinations to see if that would produce an effect. We also tried doing some runs with higher bilge water concentrations, thinking that maybe there just isn't enough solids or something just to lift off, and so we'll increase that. But for all those different variations, we still didn't see any backpulse flux benefit. The graph on the right is the results for the aluminum hydroxide, which we changed to sort of as a pod surrogate because we could control we could mix it up and control the concentration. And for the aluminum hydroxide, there was a backpulse benefit at lower rotations, but not at higher rotations. Slide 20. These are results for black water and backpulsing. And so the left slide shows the backpulsing results by disc, the 6-inch versus 10.5 inches. And as you can see there, for the 10.5-inch disc, there was a backpulse benefit at pretty much every rotation. At the 6-inch, the benefit increased as you increase with rotation. The slide on the right shows the backpulse benefits by inner and outer membrane areas. So the inner area would be represented by the small disc results, and the outer area, we did some calculations to get the fluxes for the membrane area from radius of 3 inches out to 5 1/4 inch. So the area that would be outside of that 6-inch membrane. And for the inner area, there was a slight flux benefit, and it increased with increasing rotation. For the outer area, a bigger flux benefit, but it decreased with increasing rotation. On slide 21, we started to look at the effect of radial distance and rotation on flux based on what we were seeing between the 6-inch and the 10.5 inch diameter disc. So for build water, and this is where we use those hubs of different sizes to block off different regions of the membrane. And so for build water, flux increased with rotation for all the membrane regions. If you were just to put your finger at 100 RPM at one of those rings and just to follow it as the rotation increases, it increases for every little bullseye section. But when you start looking at for a single rotation and looking at the fluxes for the different areas, you start to see some function with radial distance. So we analyzed the data using a power law relationship to relate the effect of the Reynolds number and shear rate on flux. And then using the equations that we came up with, we predicted what the flux should be for a 14.7-inch disc. That is the largest stock size that TerraFall produces. And then we bought some of those 14.7-inch discs and also built a new membrane chamber, a larger one, and then did repeated the test and saw that, as shown in the table, that our actual fluxes were actually a little bit higher than the predicted flux, and the percentage was anywhere from 5 to about 20%, depending on the rotation. So we saw probably the biggest improvement at a lower rotation. So on slide 22, same analysis for black water. Again, we see the flux increase with rotation for all the membrane regions, and we also see that variation with of flux with radio distance. So we did the power law relationship analysis, predicted the fluxes that we thought we would see for 14.7-inch membranes, and then did the test, and the results were not what we expected. And this is where we had something that we didn't expect. We had used waste from 633's liquid waste lab to do the earlier test, but then when we did perform the 14.7-inch disc, we weren't able to get any waste from them. They weren't doing any testing at the time, and so we got waste from the Little Patuxent River wastewater treatment plant, and we made sure that the percent solids was in the same range as what we'd used previously, thinking that's the main criterion. But we still got unexpectedly low results. But we think that was we don't know what it is, but we feel that the membrane the prediction should hold, but we weren't able to repeat the test to verify that. On slide 23, we did several sort of additional experiments. It was brought up in a meeting with the oil pollution abatement team in Post 633. They wanted to know if the ability of these membrane discs to exclude oil was due to them actually excluding the oil, or them excluding the oil which had absorbed to the solid. And so we did runs with bilge water of different concentrations, with and without solids. And as the graph on the top right shows, there was no effect. So we concluded that the membrane is actually excluding the oil droplets, whether or not they're attached to a solid. And then one of our goals was to also make sure that we're not giving the ship a system that needs a lot of different chemicals to clean it and things like that. And so we obtained some clean MCT, which is what the shipboard systems use to regenerate their membranes, and we used that as our cleaning one-step cleaning process. And there was a slight reduction in performance after runs after we had cleaned with MCT versus our two-step process, but we thought it was a small enough difference that the overall benefit, due to just the reduced time and residuals, would be worth it. So on slide 24, this is summarizing the results by membrane of what we saw for the different weights. I guess overall, the 60 nanometer ceramic membrane performed the best for bilge and black water, the two lower graphs. For bilge, some of the 3 micron stainless steel membrane did have a high flux, but comparing the turbidities between the ceramic membrane permeates and the 3 micron stainless steel permeates, the 3 micron probably wouldn't meet the 15 ppm or less oil content requirements. For pods, the membranes with the larger pore sizes performed better. But one thing we didn't do was we did not, Terafol does make a 2 micron pore size membrane, which we evaluated initially with bilge and some other things, but we didn't actually run it with pods. So we assumed that the 2 micron ceramic would be similar in performance as the stainless steel. So then looking at the performances by disc size for the different weights. For bilge water and aluminum hydroxide, we did show that larger discs rotated at lower speeds produced more permeate than smaller discs rotated at higher speeds. So as you can see, the dark gray triangles here and here are higher than the fluxes produced by the flows produced by the 10.5-inch membranes rotated at higher rotations. We believe the same results would be expected for Blackwater despite our data. And we still recommend the 16 the larger discs rotated at lower rotations for the Blackwater waste. So we had SpinTech build a 5-disc system that we could test the effects of, take the results and what we learned with continuous cleaning and backpulsing and see how it scales up. So we did that with a 5-disc system and evaluated it using 1x filled water. And what we saw was that the fluxes from the multi-disc system were actually higher than what they were from a single-disc system. So multi-disc are the circles and the single-disc are the triangles. So at, let's say, 500 RPM, our multi-disc, even without continuous surface cleaning, which is the black one, was higher than what we were seeing from the single-disc system with continuous cleaning. So we think that this could be due to the just increased mixing with the multiple discs. And since and like the huge benefit we saw from continuous cleaning at the smaller disc, the 10.5-inch disc, that benefit was reduced once we 10.5-inch disc in a single disc system. That benefit was reduced when it was in a multi-disc system. So it looks like once you scale up to a full-size system, that the larger disc flow benefits will outweigh the benefits you get from continuous surface cleaning for billed water. This is we are funded by CERTIP as well as ONR. This is a breakdown by project by performer. I'll move on to slide 28. For our transition, we always envisioned that there would be a place for the rotary membrane system in the Navy shipboard. In this past round of ESTCP, Code 633 submitted a proposal to demonstrate a rotary membrane system for shipboard billed water. It was, I guess, phase 1 of that proposal was funded, and that is just getting started. And the demonstration was endorsed by the tech warrant holder for environmental systems. Throughout the project, we've made sure that we've kept in touch with the wastewater management branch, the solid waste side for the pod waste, as well as the tech warrant holder and the NASTY engineering managers for these systems, to make sure that that as the project evolves, we're still in line with what the shipboard community sees as our place. We had project updates. We had some project updates on our results, and they gave us some feedback as I showed with the solids, no solids test, and we wanted to make sure that we addressed any of their concerns up front. So in conclusion, we did demonstrate that the rotary membrane system technology can effectively treat a variety of solids-bearing Navy wastewaters. We tested it on oily waste, we tested it on a biological waste, we tested it on a particulate waste, and it did well with all types of waste. We definitely developed a large body of data and a greater understanding of the impacts of flux enhancements such as continuous surface cleaning and backpulsing, the effect of disc diameter, rotation, membrane type, and the turbulence enhancement, as well as the system scale-up on, the effect of all of those parameters on minimizing the system footprint and volume. And so I think what we've done is, we've produced a body of information that will enable people to take the technology and then make decisions and tailor the system to their particular type of waste. It's really hard to summarize our actual technical results because it really varies by several different diameters or by parameters. But I think overall we did demonstrate that larger membranes rotate at lower speeds may have the best way to be able to increase your waste throughput while minimizing system size. On slide 30 just shows the publications that we produced. And slide 31, we did not have any social media. And that concludes my presentation.
Tracy, this is Rob, and at this point, I guess what I'm struggling with is, first of all, do you think this is a system that would go on existing platforms or would have to be built into new platforms? And depending on who's asking the question, if someone said to you, what should I put on my boat, could you, with the knowledge you've gained in this project, come up with here's your best choice based on money and the various parameters that you've discussed? Right.
Well, I think we'd be most comfortable recommending a system for bilge water just because we spent the most time testing on that wastewater. And certainly the rotary membrane system is something that could go on, I think it could be retrofitted to existing ships. I mean, we're, based on size, I mean, it's something that could be, could be hatchable, and I mean, they already have space designated for their current shipboard system, so if we're just replacing those, then we definitely just be able to, it could be retrofitted. And I think it could easily be integrated into new shipboard design. And as to the other ways that, I mean, I think we're fairly confident recommending maybe making recommendations for the other ways. There's just a little bit more uncertainty. They're only just starting to, I guess, shipboard evaluate black water, gray water systems, and those vary a lot from ship class to ship class, and what type of, whether they're combined wastewater or separate black water, gray water. So I think there might be a little, a need for maybe a little bit more work for some of the other ways, but I think we have a good foundation for what for those wastewaters for them to build on.
And then one more kind of comment, if nothing else, but with regard to social media, I guess there's a question here, and that question is, do you think that you could maybe provide our office with some social media, something that we could go to the public with and say, here's some of the good stuff we're doing in wastewater treatment intended for shipboard applications?
I guess you're looking for a video or for photos or
something, any and all.
Okay.
A short description, something that is publicly releasable, describing some of the research that you've done. It doesn't have to be video. It can be pictures with some descriptions.
Okay. I think we could come up with something, some photographs or something along those lines. The video, that would be more difficult.
Understand? Yeah, sometimes that's tough to do, but maybe video's not the only social media. A lot of times pictures are just fine.
Okay. Yeah, I guess I'll coordinate with Sarah or Lisa.
Yeah, and they can point you in the direction of some of the things that have been released over the last year or so you get an idea of what kinds of things we have been putting up on our blog site.
Okay.
Now, any other questions? Anybody else? Please chime in.
Yeah, this is Bruce Holden. I had a question. For the bilge water, you were using the oil monitor as your measure of quality. What were you using for the black water, gray water mixture?
For most of the black water, gray water tests, we were monitoring turbidity to make because they saw the rotor membrane system as something that would remove solids. So we were concerned with just mostly solid content. And then there were at the request of the liquid waste side at Carter Rock, we did do some grab samples to look at BOD and COD and TSS to get a feel for the how much the rotor membrane system can reduce those parameters by.
Okay, could you comment on that? How good were they at BOD, COD?
So let me just go back to all right. So I'm on slide 16. So it was the rotor membrane system was able to reduce the BOD, the COD, and the TSS to below the discharge limit. Our waste wasn't as concentrated as the ranges that the liquid side had provided to us. So I guess we can only assume that if the feed concentrations were higher, we'd be able to, again, get it down to below the discharge limit. But I feel pretty confident that even if the feed concentration is higher, it'll still bring the permeate down to dischargeable amounts.
Okay, thank you.
I guess one more either comment or question, and this is really more towards the future, but one of the things that's really important for shipboard stuff is the amount of maintenance required to keep a system running. And again, not for a research project like what you have been working on, but in the future, someone is going to have to pay special attention to the amount of time and the amount of labor that's required to keep a system like this running. Do you have any sense of that from your perspective? Do you think these are robust systems that can operate in a shipboard environment with minimal intervention?
I would say that yes, that they can that they don't need someone to babysit them, and maintenance shouldn't be that much. We weren't really. I think it felt like we had to do a lot more maintenance than you'd really want to do on a shipboard system. But then again, we were operating it in a way that we were constantly starting and stopping it. Multiple times a day. We were doing things that wouldn't be done on a ship.
Right.
And so, I think we were really.
But that gives you a sense. If you're able in the laboratory environment to start it, stop it, restart it, all that, that gives you a sense that it is a fairly robust system.
Yes, so I think it's shipboard. It could operate on board a ship without really any problems. I think in terms of maintenance, it should be comparable to the current shipboard system. And the only difference may be, cost of maintenance. The membranes that are currently used on board ship, I know, are a lot more expensive than the membrane discs that we're using.
Okay. Anyone else? Any other questions?
Yeah, this is Bill Hertel. Hey, Tracy. And plus, I would add to that even though the challenge here is the environment and the waste streams, especially if it's bilge water, which your research has shown that you can definitely perform. But these discs are used in discrete commercial applications in a system to do different waste streams, but obviously are deployed on some sort of production basis. So in that, at least that gives at least some small indication that there is some, production-oriented application of these stacked membranes. Am I correct there?
Yes.
Okay, thank you. Okay, I'm listening, and if I don't hear anything else, I'm going to say thank you very much, Tracy. Appreciate the effort you put into this. This was a successful project.
Great. Thank you very much, Robin.